So the next one is again about determinants, but also about the zero matrix. It's quite an interesting phenomenon to be seen here. We have an example of two simple 2x2 matrices. Perhaps it strikes you that one of them has a 0 column, the other, and even a 0 row, and the other also has a 0 row. So it's quite obvious that they are singular. In this case, they are both singular, but this is not so important. We are asked to prove the following. The product AB equals 0. If this is our equation, it means really 0 in the sense of a zero matrix, okay? And if we test it, okay, now what should we prove? We should prove that if this is the case, it does not imply that either A or B is itself the zero matrix. One could think it, you know, you remember the theorem of the zero product, as I call it often. In regular algebra, in simple algebra, we are used to the fact that if we get a 0, one of the factors must be 0. And in the sense of a matrix, this would mean that one of them would have to be the zero matrix. But this is not the case. And this is the point. Part one. The second part is, although no one of these matrices has to be the zero matrix in order for the zero matrix to result as the product of both, okay? None of them has to be the zero matrix. On the other hand, at least one of them has to be singular. Now, don't wonder why in this case both of them are singular. This doesn't matter so much. Let's just start. Now we multiply these two matrices. First, you remember, Urtek principle again, yeah? First row times first column, and so on. And you will see 1 times 0 plus 0 times 3, you always get 0. 0, 0, whatever you do, you get 0, you get the zero matrix. So this is a good test example. And we find that neither A nor B are the zero matrix. So this is already the proof that this that is correct, the first part. The second one is more interesting because you see here, now this is just a result from just now. AB equals 0 implies A equals 0 or B equals 0 is false by contradiction because we found a negative example. Now, why does it hold in general that one of the matrices must be singular in order for their product to get the zero matrix? And it's quite simple in the end, but well, you must see it. So it's a fact, and you know this general theorem, I think, that the determinant of a matrix product is also the product of the single determinants. You see? So calculating, this is an interesting fact, by the way. To prove it is not really trivial. It's some effort to prove it, okay? But anyway, the determinant of such a matrix product is exactly the product of the determinants of the single matrices. I say of the two matrices. With single, I don't mean singular, okay? Now, take the case, our interesting case here. If the product A times B equals zero matrix, it follows, because this is a valid equation, then the determinant of A times B must be also the determinant of the zero matrix, which is definitely equal to 0. So now that's it. We know that in this special case, the determinant of the matrix product must be 0. And using this general theorem, it means that either the determinant, now we can really use the classical theorem of zero product, because this is classical algebra now, it's simple algebra. Determinants are just numbers, they are not matrices. And that's why now this time, either this factor must be 0 or this factor. One of them is the determinant of A, the other is the determinant of B. So indeed, either A must be singular or B must be singular. And that's quite a nice result. Yeah, I told you that in the example, both are singular. Actually, I must admit, and it's perhaps it's an interesting exercise for when for the coffee break or something. Do you find any example where just one of these matrices is singular and anyway their product is the zero matrix? I have tried for a long time, not so really, but I've never found an example where only one of these matrices is singular. I only find examples where they are both singular. That would be interesting, but it can't be so hard even. You would just have to set one of the matrices as to be invertible, and then an unknown other matrix constructed in such a way that the result is the zero matrix. Interesting task. I haven't made it yet. So, but that's it for now.